students, we start with our next topic of this computational fluid dynamics. In previous lecture we have studied about introduction part of this computational fluid dynamics. So let's begin with next part. Now in next part we will study about the what are the basic governing equation, which is very important, and before this governing equation, which are the primary mathematics required to understand, then only we can proceed. Otherwise it will be very difficult for students to understand the mathematical behavior of the fluid. So that's why before understanding this mathematics, we first revise our previous mathematics to understand the governing principles. So we have already studied them. For any fluid physics, the three important parameters are conservation of mass, conservation of momentum, and conservation of energy. So the cornerstone of computational fluid dynamics is the fundamental governing equation of the fluid dynamics, which is continuity, momentum, and energy equation. And continuity equation, it is based on conservation of mass. That is momentum equation, it is based on conservation of momentum, and energy equation, it is based on conservation of energy. Okay, so these equations speak physics. Whatever the physics behind any flow, which is told by your governing mass conservation, momentum conservation, and energy conservation equations. They are the mathematical statements of the three fundamental physical principles upon which all physics of this fluid dynamics is based. So conservation of mass, conservation of momentum, conservation of energy. What is conservation? You have already studied. So very basic idea about conservation. I think you have studied energy can neither be created nor be destroyed, transferred from one form to another form only. So that is conservation. You have studied in our lower classes. So the next part, it is modeling of flow. So to model any fluid flow, the basic requirement is first choose the appropriate fundamental physical principle from the law of physics. So we have to choose either it may be conservation of mass, conservation of momentum, and conservation of energy, and apply this physical principle to suitable model of flow. So what are these different model of flow? That also we will study. Different models of flow. Generally in fluid mechanics we will study about 4 model of flow. Okay. So from this application, extract the mathematical equation which embody such physical principle. This section deal with all this item 2, that is physical principle to suitable model of flow, namely definition of suitable model of flow. So it may be infinitesimal small element, or it may be control volume approach. So in FDM, that is finite difference method, we will use infinitesimal small element approach, and in control volume, finite control volume approach, we will use finite control volume, infinitesimal small control volume approach. So these 4 models, if we see, so in this 4 model, if we see, this is our figure number 2.1, finite control volume approach, it is A. This is finite control volume approach. Okay, so second model, it is your infinitesimal fluid element approach. So see here, this is control surface and this is control volume. So it may be of any irregular shape. It is not important here. We have to make a regular shape. It may be any irregular shape. This is the advantages of control volume approach. So what is the difference between this left and right? Here both are finite control volume approach. This control volume approach is what? This control volume approach, it is fixed in space, and this control volume, it is moving with flow. Means here finite control volume fixed in space and fluid flowing across this finite control volume. So you can see here finite control volume may fixed in space with the fluid moving with it, or alternatively control volume may be moving with flow. So we can see this is a part of flow. Control volume, this is part of flow. You can see this is part of flow. Flow and control volume, these are not two entities. Complete flow and control volume, this is one only. Okay, so this is the difference in between these two models. This is fixed in space and this is flowing with fluid. So control volume flowing with fluid, control volume fixed in space. Second, that is infinitesimal small element. It is fixed in space when it is fixed in space. Okay, fluid flowing across this element, and this is when infinitesimal small element moving with flow, means flow with infinitesimal small element. So these are not two entities, we consider complete entity. Okay, flowing. Okay, this is the difference. So in this way you can see these are the four models of your model of fluid flow. Okay, so next important, the equations obtained for finite control volume fixed in space, that is we have seen in 2.1a left side. So there integral or partial differential form are called conservation form of governing equation. So what is conservation form of governing equation and non-conservation form of governing equation, we will understand later, but here you can please remind it that your finite control volume fixed in space, it is conservative in nature. So conservation form of governing equation. Okay, finite control volume fixed in space, and the equation from finite control volume moving with flow, it is either integral or partial differential equation. So generally when we use finite control volume approach or FVM approach, in that case we use integral approach, and when we use FDM method, that is finite difference method, then we use partial differential equation. Okay, so that is the difference. So partial differential form or integral form are non-conservative form when finite control volume moving with flow. Next to this, that is aerodynamic theory. If we see non-conservative form of equation is irrelevant. Why? Conservation and non-conservation, this differentiation is irrelevant here. Why? When we do any mathematical interpolation or mathematical exercise in our fluid flow phenomenon, in that case mathematically you can convert one form into another form very easily. If you have mathematical understanding, so conservative form can be converted into non-conservative form, and non-conservative form can be converted into conservative form. So these are interrelated, and there are the cases in CFD where it is important which form we use, and nomenclature which is used to distinguish this form only. So conservation versus non-conservation. So that you can see in your primary CFD literature. Okay, so have you understood this, that conservation form, it is fixed in space, non-conservation form, it is moving with flow. Okay, so it may be your finite control volume approach, or it may be your infinitesimal small element approach. Next important, substantial derivative. This is basic about your mathematics. Substantial derivative, another name for substantial derivative, it is material derivative also and total derivative also. Okay, so let us assume three-dimensional case, u, v, w. U, it is x direction velocity, v, y direction velocity, and w, z direction velocity, and these are the function of x, y, z, t. Okay, these are x, y, z are space, and t, it is with respect to time. Okay, so we are considering in general unsteady flow where u, v, w are function of both space and time. Okay, so in addition the scalar density field is given by rho. So because here density we consider scalar, so that's why we can use rho also. So rho is also a function of x, y, z and t. It depends on your flow. If it is incompressible, so we can consider density it is constant, and if it is compressible, so density will vary. So let us see the derivation part about substantial derivative. So this is about your basic understanding of mathematics only. So it is required first. That's why I am taking this part. You may know this part, but for primary understanding it is required. Okay, so here let us assume this is one point or state. From this one point to this 2 point fluid is flowing, let us assume, and this is initial time t1 at initial x1, y1, z1 space. This will be this will be your x1, this will be your y1, and this will be your z1. Okay, so similarly your x2, y2, z2 will be position number 2 and t2 time. Okay, so fluid is flowing from this 1 to 2. So if I have to write the equation for density difference from this 1 point to 2 point, so how I can write? With the help of your Taylor series expansion. So this is all about Taylor series expansion. So rho 2 it is equal to rho 2, it is equal to rho 1 plus whatever the changes occur. So changes occur in x direction also, y direction also, z direction also, and with respect to time also. But what is this higher order term? This higher order term means if we see the difference, so here we are seeing only first order, that is delta x, x2 minus x1. If we again differentiate it, so del square rho by del x square and x2 minus x1 whole square upon 2 factorial. But that part again 3 factorial, 4 factorial, 5 factorial. So infinitely there will be change, or in very small range it will be very small. So that's why we neglect, and this will be considered as higher order term. So in y direction also, z and time also. So that's why this all higher order term we neglect, and this creates one type of error, that is nothing but your truncation error. Okay, so if we divide this t2 minus t1 with this complete equation, so you will get this equation. You can see rho 2 minus rho 1, this rho 1 will come in left hand side, so rho 2 minus rho 1 upon t2 minus t1, and then you can see x2 minus x1 upon t2 minus t1. This is your x direction velocity if we apply the limit delta t tends to 0. Similarly, limit delta t tends to 0, this will be your velocity in y direction. Similarly, this will be your velocity in z direction, and here this will be as it is. So next, that is limit t2 tends to t1 if we apply. So you can see this t2 tends to t1 you can write, or you can write delta t tends to 0. It will be same. Okay. So d rho by dt, this is nothing but your left side, and after this right side you will get, this will be your right side, this will be u del rho by del x plus v del rho by del y, and w del rho by del z and del rho by del t. So this is what? This is your total derivative of density. So you will see this part, this is space with respect to x, y, z, this is space, and with respect to time, so this is with respect to time, so that's why this is called as local derivative, and this is called as convective derivative. Okay, so these are the two parts in this total derivative. One part it is local derivative, another part it is convective derivative, and completely capital D by capital dt, it is called substantial derivative. So you can see this substantial derivative, it is equal to summation of local derivative and convective derivative. What is del sign? This is normal calculus, vector calculus part, that is I del by del x plus j del by del y, k del by del z. This is nothing but your operator. You can see if we separate out this part, ui plus vj plus wk, so this will be v velocity, this will be your v velocity, this will be your v velocity, this will be your ui plus vj plus wk, and del by del x plus del by del y plus del by del z I j k. So this will be dot product, and finally you will get v dot del. So this del operator, it is represented by this, and v, this is represented by ui plus vj plus wk, and this is local derivative, and this is convective derivative. Okay, so this is all about total derivative part. So thank you for today. So in next lecture we will understand about conservation of mass principle, then next we will see conservation of momentum, and then conservation of energy. So likewise we proceed our CFD syllabus. Thank you very much.